Have you ever wondered why engineers can't just kind of guess their way through a calculation? I mean, think about it. One tiny error in a limit could literally mean a failed mission. Today, we're taking limits from pure guesswork and turning them into absolute certainty. Welcome back, future doctors and engineers. Are you ready for a new mathematical thrill? Let's go.
So in our previous explainers, we comfortably threw around phrases like as x approaches a. But honestly, in high-precision engineering, that's just way too vague. Precision is all about error tolerance. We need to absolutely guarantee that close enough is actually exact. We can't just rely on our gut intuition when lives are literally on the line. We need rock-solid proof.
Section 1. Absolute precision. Guesswork to precision.
Stewart's text actually illustrates this perfectly using a machinist. Imagine a machinist who needs to manufacture a circular metal disc, and it has an exact target area of 1,000 square centimeters. Now, they are allowed a tiny error margin, but to stay within that margin, they have to perfectly control their input, which is the radius. You see, they can't measure the area directly while they're cutting it on the lathe. They can only manipulate that radius.
And that brings us to our first key player, epsilon. Epsilon represents that strictly allowed tiny error tolerance for the disk's final area. It's basically the uncompromising boundary that the final product has to stay within. If it helps, think of epsilon as the absolute maximum mistake the client will tolerate. It is the boss of this entire operation.
Now, to control that output, we have delta. Delta is the tightly controlled safe zone for the input radius. If you keep the radius within that super tiny delta distance, you guarantee the final area won't exceed the epsilon error tolerance. Delta is basically the mathematical answer to the epsilon problem. It's the precise physical control the operator has to maintain on the floor.
Section 2. Mathematical symbols. Decoding the code.
Okay, let's look at this symbol here. The absolute value f of x minus L is less than epsilon. Now, what does that actually mean? It simply means the distance between the function's output and our target limit must be strictly smaller than our error tolerance. We use absolute value here because, well, distance is always positive, right? We just want to know exactly how far off we are, period. But how do we actually guarantee that? Well, by picking a safe zone for our input x around our target number a. We call this zone delta. And notice it's strictly greater than 0. That's because we only care about what happens around our target, not exactly at it. We're analyzing the mathematical approach, the journey toward the limit, not the destination itself. So, here is the plain English translation of the formal definition. If you can keep your input x within the delta safe zone, I promise the output f of x will stay trapped within the epsilon zone. If this works for any epsilon, no matter how microscopic it gets, then boom, the limit exists. It's basically an ironclad mathematical contract between your input and your output. Wait, stop right there. I want you to pause this explainer for a second and really think about this. If we make our error tolerance, our epsilon, even smaller, should delta get larger or smaller? Think about the sensitivity of the function here. If you need a much more precise output, you inevitably need a more precise input, right? So delta has to shrink. Make sense? Okay, let's keep going.
Section 3. Algebraic rescue proof. Finding delta.
Let's prove this just like the giants of math did. We want to rigorously prove that the limit of 4x minus 5 as x approaches 3 is exactly 7. We're going to start a little algebraic fight to uncover the perfect delta for any given epsilon. We aren't just blindly plugging in numbers anymore. We are building an unbreakable algebraic relationship. All right, step 1. We start with our output inequality. The absolute value of 4x minus 5 minus 7 is less than epsilon. Step 2, we simplify inside the bars to get 4x minus 12. Step 3, factor out the 4. And step 4, divide by 4. See what we did there? We simplify until the absolute value perfectly matches x minus 3, which is exactly our input target.
Boom, we found it. Our delta safe zone must be exactly equal to our epsilon error tolerance divided by 4. No matter what crazy epsilon someone demands, we now have our guaranteed formula. The algebra literally did all the heavy lifting for us, completely removing the need to ever guess again. So, in the real world, if someone demands an exact precision, say, an epsilon of 0.01, you don't guess. You just divide it by 4 and confidently hand them back a required input safe zone, a delta of exactly 0.0025. You've just mastered the Epsilon-Delta proof.
Honestly, you could hand this over to any engineer with absolute confidence.
Section 4. Golden Tips, Mr. Math's Advice.
Now, to absolutely ace your exams, you've got to remember these Stewart-style tips. First up, the graph trick. If you're looking at a drawing, delta is always the shortest distance from your point A to the edges of the interval. Second, the greater than zero rule. This just means we don't care what happens exactly at the point, only around it. And finally, Cauchy's legacy. Augustin Louis Cauchy created this exact rigor to finally end the era of guessing in calculus.
Section 5. Epsilon-Delta Challenge. Test your skills.
Challenge time, heroes! Take a look at these parameters, drawn directly from Stewart's exercises. Your function is the square root of x. Your limit is 2. A is 4, and your allowed error, epsilon, is 0.4. Now, based on everything we've covered, can you calculate the exact value of delta that keeps the function perfectly inside the box? Because today we officially tamed the Epsilon-Delta monster. We took a concept that usually causes total panic in calculus students and completely replaced that fear with the absolute power of mathematical precision. So, did you solve the challenge? I want to see your genius in the comments below. Don't forget to support the channel with a like and share so you can catch the new MR Math identity on all platforms. Thank you so much for joining me, and I will see you in the next mathematical thrill.